Greetings, mathophiles, and welcome to a discussion of the relationship between the differentiability and the continuity of a function at a given point. We're going to begin with this cubic that you see in front of you. For the record, it's g of x equals x cubed minus 3x squared minus 9x plus 10. As a polynomial, it's going to be continuous everywhere. That's a fairly easy result to prove. We're going to examine a particular value, x equals 2, so this is the point 2, negative 12, or 2, g of 2. And we're going to then identify another generic point at x equals x naught somewhere on this graph. So we have points at x equals 2, we have points at x equals x naught on the graph of g, and we're going to make a secant line connecting those 2 points. Now, a derivative is nothing but a limit of a secant slope. So if I take a look at the slopes of the secant lines as x naught approaches 2, we'll want them to be consistent with one another. We'll want the limit to exist from both sides, and we'll want the limits to be identical. And you'll see down here in the lower left the slope of that secant line displayed in a little box. And so I'm going to bring x naught closer and closer and closer to x equals 2 from the left. And you'll find that the slope of the secant line is in the neighborhood of negative 9. If I do the same thing from the other side, if I let x naught approach 2 from the positive side, I find also that these secant slopes are in the neighborhood of negative 9. If you were to actually take the derivative of g and then plug in a 2, you would get the value of negative 9. So here's an instance where function is continuous at that location, differentiable at that location. Here is another function with a rather noticeable discontinuity at x equals 2. For x less than or equal to 2, this is the same cubic that we saw a moment ago. For x is greater than 2, this is the line y equals 8/3 x. So if I call this function f, this function is clearly discontinuous at x equals 2. Let's ask ourselves the question then, can it be differentiable at x equals 2? So we will go through the same exercise. We will highlight f of 2, and it belongs to the left-hand branch rather than the right-hand branch because of how we structured the inequalities. We will choose a generic point elsewhere on the graph of f, and we will make the secant line, and we will display again down in the lower left the slope of that secant line. Now, unsurprisingly, when we are plugging in values to the left of 2, slightly to the left of 2, we see things happening pretty much as they did in the first example because it's the same function to the left of 2 and at 2. So the derivative, if you will, from the left, the secant slope, is in the neighborhood of negative 9. However, when x naught is a little bit greater than 2, there is a big whopping disagreement between what the difference quotient, slope of the secant line, however you want to refer to it, is doing on the left and on the right. And if the limit of the difference quotient does not agree on one side of 2 as compared to the other side of 2, then that unrestricted limit can't exist, and the unrestricted limit is the derivative. So the derivative doesn't exist. So here is at least one instance of a case in which a discontinuity in a function prevents that function from being differentiable at that location. It would be interesting if we could figure out whether that would always be the case, that if a function is not continuous, then it's not differentiable. The contrapositive of that statement, which would then also have to be true if it were true, is that if a function is differentiable someplace, it's got to be continuous someplace. Turns out that's true, and we're going to turn our attention to a statement and then a proof of that little theorem. So here's a statement of the theorem suggested by our graphical examination on Desmos. If f is differentiable at some value x equals x naught, then f should be continuous at some value x equals x naught. And the fact that I just boldly stated it as a theorem is pretty suggestive of the fact that it's going to end up to be true. And here's a little proof, and the proof is rather slick. If f is differentiable, then we know that the limit that corresponds to the definition of the derivative has got to exist. So the limit x to x naught of f of x minus f of x naught over x minus x naught exists. It's a real number. If it's a real number, we can multiply it by 0. Only here's how I'm going to write 0. I'm going to write it as limit x to x naught, x minus x naught. That certainly is the number 0. And whatever this was times this, since that second limit is 0, has got to be equal to 0. If these two limits exist, and they do, then I can use the fact that the limit of a product is the product of the limits, and this becomes limit x to x naught f of x minus f of x naught over x minus x naught times x minus x naught. And that's still equal to 0. Now, as long as x and x naught are not equal, these differences are non-zero, but they are identical, and so their quotient is 1, and I can cancel them, as the saying goes. So now we have limit x to x naught of f of x minus limit x to x naught of f of x naught, because the limit of a difference is the difference of the limits. But f of x naught is a constant after all. So I should just be able to write that as f of x naught. So limit x to x naught f of x minus f of x naught equals 0, or equivalently, limit x to x naught of f of x equals f of x naught. But friends, that is the definition of f being continuous at x equals x naught. How did we get there? By the assumption that this was a real number, by the assumption that it existed, but that was equivalent to assuming that f was differentiable. So, if a function's differentiable somewhere, it's continuous there. And since we build up differentiability and continuity on intervals based on differentiability and continuity on individual points in those intervals, if f is differentiable on an interval, then it's continuous on that interval. Now, is the converse true? Is it the case that if a function is differentiable, it must therefore be continuous? And the answer is a big thundering no, because of things like this. Situations where there is a connectedness, but certainly the difference quotients on the left-hand side and the right-hand side are not doing the same thing. So, differentiable function must be continuous. Continuous function may or may not be differentiable. Hope this has been interesting. Happy mathing.